Okay, welcome back. Now we have an invited talk from Professor Manfred Opper from Technical University of Berlin. And the title of the talk is Approximate Inference for Continuous Time Markov Processes.
Yes, thank you very much, and I'd like to thank the organizer for inviting me. It's a list of my collaborators, and a couple of them are here, and so hopefully they can help me out for any problems that I might have in explaining things or understanding things. And yeah, some of my approximations will actually be variational ones. So probably from the previous talk it might look like maybe they're just all going down, but let's see. It's not the end of them, so we're not giving up. Right. So what's interesting about Markov processes? They seem to be fairly simple objects compared to other things that we're interested in machine learning. Very loopy type of things. So this is seems to be a simple thing, a Markov process. So I think the complexity here is coming from the fact that it's a continuous time. So what's a typical problem that we're interested in? A toy problem here. So we think we have a time series here, and it's in continuous time, but we only observe the variables at certain discrete times. And here it's a bivariate time series made up from a toy prey a predator problem. So we observe these at these times, and there's an underlying model which I'll talk about in a second, and also we have a couple of parameters in the model which we don't know. So the problem would be inference of these parameters and maybe find out what happened in between the points, and maybe the points were also a little bit noisy, so we don't exactly know the value of the state variable. So the underlying model was something like that. There were preys that multiply with a certain rate proportional to how many people you already have. Preys will die with a certain rate depending on how many predators and preys there are around, and similar type of things. So it would be, in this case, a so-called Markov jump processes, because the number of preys and predators would be integer variables, and they just can go up and down in discrete steps and things like that. So this would be actually the underlying simulation of the underlying process. So we have these little jumps here, and these were the parameters in that case. And sort of this is the kind of things that we try to find out. Another type of example is another toy model. Here you see again, this is time. This is now a univariate time series, and again you have observation at discrete time points, and again you try to fit like a prediction, a mean prediction through it, and you also try to figure out what's the uncertainty. And in this case, the red thing is what we believe is a bad prediction because it's only a data-driven one, and we were using a Gaussian process Gaussian process regression method to fit this curve through. And of course, it would say if you're very far away from the observations, then your uncertainty goes up. And well, if you know something about the underlying model, you might actually do better. And in this case, the underlying model is a so-called stochastic differential equation, and Yuan Shen in the talk this morning already introduced these types of things. So the little change in the state variable over time is given by a so-called drift, and there's a white noise thing adding to it, a diffusion. So the drift in this case is the negative gradient of a potential, and its potential is a double well one. So this thing means if there's no noise, then the state will always relax in one of these two local minima, but then it's always kicked by that stochastic force, so it might just, do kind of a little bit of Zitterbewegung in this type of thing, and then from time to time it might flip on the other side and then continue and go back and forth. So that means based on this observations and based on a Monte Carlo simulation, that would be actually the best mean prediction you could make. It's the blue curve, and that would be the base. Well, that would be the error bar if you know the parameters perfectly. So because we know for a long time we're going to stay in that area, so the uncertainty is not anymore blowing up. So that would be the optimal prediction But the underlying sample path might actually have looked quite rough compared to the mean prediction, so there's no, that's not a problem. The mean prediction is still smooth, but the underlying sample path might have looked like this, infinitely often, well, non-differentiable at all. I mean, in contrast to, for instance, a Gaussian process with a smooth kernel. So that's the type of problems, and here's the overview, the things that I might be able to talk about. So first I'll introduce a bit more formally what these partly observed continuous time Markov processes are. Then I move on to an exact inference. So what would we have to do exact inference? Of course, when we hear about Markov things, forward-backward algorithm, right? So how would that look like? Then we do a very simple approximation based on assuming, well, linearizing, right? Weak noises, not much fluctuations, maybe we can get away with linearizing, and then we'll talk about variational approaches, one in general and one related to diffusion or jump processes. So mathematically, we have two types of models here. We have both cases Markov processes. So in the first case, we assume we have discrete states, and the probability of moving from a state x to x prime during a small time interval delta t scales in such a way it means this is a Kronecker delta. It says it's 1 if we're in the same state, and there's this little change in delta t, so if you wait a little, then there is a probability of going from x into another state, x prime, and this f is called the transition rate. So it's a way of scaling the probability of going somewhere else during a small time interval. And the diffusion process, I mentioned before, is something that's governed by a stochastic differential equation. We have a state variable that is driven by a drift term. That's a deterministic part. So the change is linear in the time delta t, but there's also a diffusion part. So you add a bit of white noise into it, and the size of the white noise might actually depend on the state or on time. And so if you try to understand this, it's always useful to discretize it in time, so the actual change of the state variable has a part that's linear in delta t, again the drift, but something that goes with square root of delta t to get these nice rough diffusion parts, where this is just, independent white noise. So you can always think in terms of this discretized version, and then at an appropriate place you just go to the limit of finer and finer discretizations. All right, so that's the model. And the inference problem is, of course, we have some noisy observations of the process at certain times ti, discrete times, and we try to estimate x of t in a time interval. And it's not filtering. I mean, yesterday we heard a couple of talks that were about filters. So you just move along time, you get new observations, you update your posterior. In this case, it's really, you have a fixed time window, you have the observations, and now you work on the posterior and try to predict overall time what has happened also in the past. So it's not the filtering, it's the smoothing problem. And then, of course, if you have parameters that you don't know, for instance, in the rates or in the diffusion drift, you try to estimate them. Right. Yeah, of course. Well, that sounds like a hidden Markov model, right? I mean, you have states that are Markov, then you have some kind of observations, so it's a hidden Markov model. There must be a forward-backward algorithm. So how should that look like? Yeah, so there's a textbook solution. So if you're interested now at the marginal posterior at some time t of the state variable x, based on all the observations that you have. Then, using Bayes' rule, you can sort of split it into a term. I would call this the forward part, where you take all your previous observations previous to time t. And then you have to multiply it by a term which is the likelihood of the future observations given the present state. So you look at those two things, and then you see, oh, the first one fulfills a so-called forward equation, the second one fulfills a backward equation. And what are forward and backward equations in the case? Well, I only discussed the diffusion case here. Well, we know yeah, we have to go in continuous time, and it's a so-called Fokker-Planck equation that tells you, at least between the observations, that this forward probability density moves according to such a what's it called? A partial differential equation with the drift f, right? And the other guy fulfills a backward equation. It's also known as the Kolmogorov backward equation. It's another partial differential equation, again with the drift here. So it's the adjoint equation, essentially, with the adjoint operator. And so you have to solve PDEs. So that's the problem. And then, of course, when you have an observation, there will be certain jump conditions, which is, you see there's always then one guy added to it. So there will be some jumps, and it's quite intuitive what's going to happen. So these KSP equations have been formulated, I think, in the signals literature by many years ago by Kushner, Stratonovich, and Pardue. So they're known as the KSP equations. Yeah, so you see, the marginal posterior is a product of two functions, and well, I don't know if if it has been used quite a lot of time, and we weren't quite sure. We could actually look at the equation that is obeyed by this product. So if you differentiate the product, it's got a nice form, you see. It actually, the posterior, the marginal posterior, fulfills also a Fokker-Planck equation, but it has a slightly different drift. So the diffusion terms are the same, but the drift is slightly different. Now the drift is given by the drift without observations and something that goes linear with the diffusion, and here's a gradient of something I would call a negative potential, where the psi's are a solution to the backward equation. So in some sense you can interpret this as saying, well, given the observations, the process is still a Markov process. I mean, if you look at this as a graphical model, you have these observations that don't destroy you this chain-like structure, and so it's going to be a Markov process, but the Markov process knows that there are observations, and if you're far away from an observation, then this term will be 0. And if you approach an observation, then, well, the process has to move closer to the observation to make it reasonably likely. So this type of minus log psi seen as a potential is something that is the influence of the observation and tells you how to move the path based on the observations. So now you could think about ways of, can we sort of try and find out what this guy is? Can we calculate it? Of course, we can calculate it using the backward equation. And in the simplest approximation that we were using is, well, linearize. And we linearized the backward equation. So we said, well, we assume that maybe this diffusion term is not very strong. And so we put a little bit epsilon here, and then assume we have a scaling form that the solution of the backward equation looks like a Gaussian. Of course, the solution of a backward equation is not a probability density, so I'm not really talking about a Gaussian density. I'm only talking about something that is e to a quadratic form, and it has something which doesn't normalize it to 1. So if you go into the ODE, into the PDE, then you get equations for this, pseudo variance and pseudo mean, and it turns out that this pseudo mean is a solution to the dynamical equation without noise, and this sort of tells you a little bit what the noise does. And well, in some sense, even this simple approximation works fairly well. So that would give you a solution just by solving a couple of ODEs for an approximate solution for the backward equation. And if you do also a linearization for the forward equation, then everything ends up in solving ODEs. Just one backward, you start at the latest time, you include all your observations, and then you have computed your new drift term, and then you get from this the forward development. And in this simple prey-predator model, where we assume we have lots of preys and predators, so you can do kind of a continuum state approximation, so you replace it by an appropriate stochastic differential equation. So you can try and do predictions. So this is the mean prediction, and here's some error bars, and it seems to be fairly reasonable. This Gaussian assumption, the pseudo-Gaussian assumption, the linearization assumption, is in some cases nicely fulfilled if you are a bit far away from extinction. Of course, if you're extinct, then the Gaussian assumption is probably not so good. But in other areas, you might be able to do fairly well. So this is kind of an average over many different realizations of the stochastic process. And we did a parameter estimation for this kind of thing using maximum likelihood and compared sort of the uncertainty based on the likelihood function and compared it with the true uncertainty that you have when you repeat this experiment with many different parameters and many different realizations. So it seems simple things can work in that case. But this actually breaks down completely when we talk about models like this double well potential where you have multi-stability. And one of the reasons is actually when you solve the backward equation in this type of thing, it's almost like solving the forward equation with an inverted potential. And sort of if you have this double well things, then all kind of nasty things can happen in that case. I don't want to explain this in more detail. So there might be other approximations that are related to Gaussians, and maybe we can get away with variational Gaussians, right? So it's we come back to variational things. So maybe we have a simple approximation, but maybe we can use it in a variational way to put it right where it should belong. Yeah, variational approximation. We discussed this already this morning. Let me see, where are we? Yeah, the problem is now when we say variational Gaussian, the moment I was always speaking about marginal things, marginal probabilities. What's the marginal density of the state at a certain time? But when we talk about the variational approximation in machine learning, usually we talk about multivariate things. We talk about the posterior distribution over all the state variables in the system. But now, since we have a stochastic process, the state variables are the state variables at all the time. So if we go to continuous time, this is essentially a probability distribution over an infinite variety of objects. Well, of course, you can think you discretize it. At least it's a probability over something that is quite large. And when I mean now a variational Gaussian, I mean a variational Gaussian approximation over that infinitely many variables, all the state variables at all the time. So that's what I mean, not a thing that just approximates the marginal. So, with slight abuses of notation, I never know what's the right notation in case of infinite dimensional objects. So I thought the safe thing is always not writing p's, but put a d in front of it, dp's. So it's what people call Radon-Nikodym derivatives, which I don't know precisely what they are. I have a vague idea what they do. So I'm interested now in sort of this probability measure over paths, condition on the observations relative to the prior probability measure over paths. When I say prior probability measure, I mean the one that's generated by the stochastic differential equation. Then the observations come and the prior is converted into the posterior. Well, so these, of course, the prior times the likelihood, that's what we have here, so that comes from Bayes' rule, and Z is a normalizer. And I've just written it in a somewhat innocent way. There's sort of this probability over infinite dimensional things, and I don't know how to really deal with it, so I said the ratio is kind of something well behaved. Right, so it's this partition function, and well, the partition function is actually the probability of the observations given the parameters, and if we had it, then we could do parameter estimation either by maximum likelihood or using Bayes if I had a prior. So that's now what we want to approximate. This posterior is what we want to approximate, but unfortunately already the prior has to be approximated because usually if it's a nonlinear drift term, the prior is non-Gaussian. So already the prior makes a problem, even if the observations would be just Gaussian noise observations. The whole problem comes from the prior. We don't know how to deal with the prior. Right, but at least we know something. The posterior is a Markov process. And so that means if we have a diffusion, there is an effective drift, and we already discussed how that drift would look like if we could compute it exactly by solving a backward equation. So there is some effective drift that takes into account the observations, and actually the diffusion is not changed. And if we had a Markov jump process, then there would be a new rate function also indicating that there are data. And now we want to sort of make a Gaussian approximation to the posterior process. You can already guess what's going to happen. If you need a Gaussian process, then this should be replaced by an effective linear stochastic differential equation where this is going to be a linear function of x, and of course the g has also, the effective g must be depending on time, because we have these observations that have to take these specific time points into account. So here's an example, a very simple example where you can see what the observation does. So this is a solvable case, so I just assume a priori there's no drift in the system, it's just a Brownian motion, and I happen to see this Brownian motion, I happen to observe it at the last time step that it has reached again its origin 0. So it's coming back, it's diffusing, and it goes back to 0. Here's another sample path of the same posterior process. They all have to go back to 0. And let's make the assumption there's no noise. We are completely sure that the process goes back to 0. And it turns out, if I do this computation, then this posterior process has a drift, and the drift guarantees that the guy is going back to this point, and it really has to go back, so it has to become very strong if I'm at the final time t. If t is equal to t, then really I have to make x small in order not to blow this up. So this is the appropriate drift, and you can compute the drift solving the backward equation, but this process is also known as the Brownian bridge. The Brownian bridge is the ordinary Brownian motion conditioned on an observation at the time point. Right, so in general, now we would use the ResIP that we know from the variational method as explained today. We would love to minimize the Kullback-Leibler divergence between the posterior and some tractable prior distribution, some practical trial distribution Q. And again, this can be formulated in a so-called minimization of a variational free energy. We have seen this before, which is now written as the Kullback-Leibler divergence between Q, which is the posterior the posterior approximation, and the prior, and a term that comes from the data. So you split the posterior into two parts, into a prior part and into a likelihood part, and then you have to minimize these two things. So the only question is, again, what is this Kullback-Leibler divergence between these measures over paths? So that is the slightly non-trivial part. So just one comment. Here's a statistical point of view, and I'm saying this because it might help actually to in the future to improve on the variational approach. So often you have in statistical physics Gibbs distributions, and here's Q, a simpler Gibbs distribution with some Hamiltonian H0, and then the variational free energy can be written as minus log partition function is equal to the one that you can compute plus a correction term. And it seems like this is something like the difference between this H and H0, but you can view this as a kind of lowest order perturbation expansion with respect to the difference between H and H0, and you can actually compute, if you want, corrections to it, and sort of that. Okay, sorry, there should be an approximate here. So you might be able to compute corrections to it that might improve on the variational method. That's just one comment. So coming back now to computing the free energy for the case of diffusions. Well, why? It's not so complicated because we can use the Markov structure for computing Kullback-Leibler divergence, and well, the heuristic method, though not the fully rigorous method, the fully rigorous method would use really stochastic calculus, and we can do that as well. But I mean, just to understand what's going on, you write probabilities over discretized paths. That's easy, right? So we know probabilities over a path sequence. If we discretize and we have a discrete time Markov process, then the Kullback-Leibler divergence is given by that term. And now using the fact that we can write the probability over this sequence as a product over transition probabilities from one state to the next one, we observe that we end up with a simple expression where we have the Kullback-Leibler divergence between the transition probabilities, and we have to average over the marginal probabilities. So the only thing that we need for this calculation is the Kullback between transitions and the marginals. That's all because it's Markov. And now, if we know how these things behave for short time distances delta t, and you see here's this sum over all times, then somehow the sum approaches an integral, and we get the result. So what we can use, for instance, for stochastic differential equations, we know that this transition probability is, for small times, just a Gaussian. And so if we plug this in, we get the result. And the result is the following thing. It's a very intuitive result. It says the Kullback-Leibler divergence between two measures q and p, and so they correspond to stochastic differential equations with two different drifts g and f. But they must have the same diffusion. If they have different diffusions, then the Kullback-Leibler is actually infinite. Because if you have two different diffusions, then they have the paths have different roughnesses, and the two probabilities are not absolutely continuous. Or what's the stochastician's name for it? So really, they have to, in order to make this work, you have to have the same diffusion. So the Kullback-Leibler turns out to be just something like an L2 distance between the two drifts. So you just take the difference of the two drifts. You have to weight it by the inverse diffusion matrix, and then average this over the marginal distribution of the Q, and then average over time. So it's just how different are the two drifts under the marginal distribution Q. So now we have the variational problem. We have to solve the variational problem. The variational problem is this: minimize the variational free energy. So we see what we get. So we have the original prior drift here, and this is the posterior drift. And this term says, well, the posterior drift should not be too far away from the prior drift, but also it shouldn't be too far away from the data. So you have to satisfy these two things. When there is a data point, the path should be close to a data point to make it likely, but it shouldn't go too far away in terms of the drift term, and so you have to optimize that drift term to minimize this thing. So it's kind of an optimal control problem. And the only thing you have to do when you just do this variation, you have to see that the drift and the marginal, they are coupled to each other, because the drift and the marginal are connected via the forward equation, via the forward Fokker-Planck equation with this corresponding drift. And now everything is very natural. You write down a Lagrange function where you introduce the Fokker-Planck equation as a condition, and then if you do this variation, you actually recover the original results that I was showing you before, the exact backward and forward differential equation known as the Kushner-Pardue KSP equations. So you can, of course, if you do a full variation using the variational method, you should end up with the exact result. Now you can do approximations in that. And as I said, one of the natural approximation is replace the true posterior process by a Gaussian process. So rather than thinking of general drift terms, we think of, well, this is just a computation. Now we want to do a Gaussian variational approximation and replace the drift by a linear drift. This is just a comment on the Gaussian variational approximation in 1D, and very often if we talk about variational approximation, people might confuse it with a totally factorizing approximation. But as you know, when I do a linear stochastic differential equation, we keep, of course, correlations, dependencies over time in this approximation. We're not doing a factorization over time. And this is well, I mean, the Gaussian variational approximation has been used by a couple of people, but I think it has been used by far less than the factorizing one. So this is just a few citations of its use in other circumstances. And here in the 1D case, what it does is, here's a density, and this green one would be a Laplace's approximation to the density which is just a local one, and the blue one would be the variational approximation. It's a non-local one that takes into account a bit more of the probability mass. But that's 1D. We want to do it kind of in infinite dimensions. So the way we do it is we replace the true stochastic differential equation by an approximating one having functions to be optimized. And the functions to be optimized were introduced this morning by Yuan Chen. So it's a function a of t, and it's a bias b of t, and these are the two things that we have to optimize now. So if we plug this into the variational method, and I don't want to go into details, but it should be clear now, it's just two functions, and we know that Gaussian measures, so if you look at the variational principle before, you see everything depends on marginal probabilities. So if we talk about Gaussian measures, it will be only the mean and the covariance that will sort of enter the calculations, and it should be clear that now the partial differential equations that we had to solve in the exact backward-forward algorithm are replaced by ordinary differential equations that we have to solve. And there's a bunch of ordinary differential equations to be added for the Lagrange parameters. So I skip the details, but it's in the world of ODEs that you have to solve rather than partial differential equations. And so coming to one of the examples, the double well potential. This is something that has been shown this morning already. There is the comparison between a Monte Carlo simulation and the one that we got out of the variational approximation. So it seems to do fairly well with respect to the mean. Again, we have this effect. We underestimate the uncertainty, but again, there's not a general proof that this always has to be the case. We can do an estimation of the diffusion constants, for instance, by computing the likelihood based on the free energy, and it's again a comparison to a Monte Carlo result. So it's not perfect, but you see at least we seem to have the maximum close to where the true maximum is, and also roughly the width seems to be quite similar. Of course, I mean, it wouldn't be science if there weren't counterexamples. It can't always work because it's a Gaussian approximation, right? I mean, if you try to approximate something which is really non-Gaussian by something as Gaussian, it shouldn't work so well. So you can, in the case where the data have a lot of noise, then of course the data don't tell you very much in the double well potential where you exactly are. So in this case, you might have a marginal posterior that has actually three local maxima. So, and sort of in this case, we don't even get the transition right, and we really underestimate the uncertainty. Again, blue is exact versus green variational. So if you apply to something that's really non-Gaussian, you can't expect that it would work. Well, you can apply it to slightly higher dimensional systems like the noisy, the Lorentz system, which is the three-dimensional a set of 3 nonlinear differential equations, and we add a bit of noise onto it, and then compare different algorithms like the unscented Kalman smoother to it. And you see that doesn't really work so well. You can do Gaussian process regression. Well, yeah, you see there's a few things that don't look so good, and the variational smoother seem to improve quite a bit on these other methods. At the moment, we don't have a comparison with the Monte Carlo, but we'll get one soon. Right, so that's about the Gaussian approximation for stochastic differential equation. I promised I would say also something about Markov jump processes. So what could we do in a case of Markov jump processes? Again, for Markov jump processes, we have a discrete state space, and if we want to have it discrete and not do an approximation by a stochastic differential equation, because we have a small, let's say, a small number of species in the model that we were discussing, a small number of molecules in biological applications. So we really have to stick to the discrete case, which is quite important. Then one idea would be, if we have many coupled things, we could go to a mean field approximation, but now mean field between different species, but not over time. So it would correspond to one of the approximations that we had before, the coffee break, factorize between different systems, but not over time. And we've done that, sort of that gets kind of the sort of originally the backward-forward algorithm would now be a set of linear ordinary differential equations in S to the D variable. So D is the number of components of the system, S is the number of states, and then we would get it down to S times D. Sort of that would be the simplification. And I'm not showing results here. We had one in the poster yesterday, but I want to show another application to that. So just briefly, what we're using for Markov jump processes is a Kullback-Leibler divergence, again, derived in a similar way. Short time approximations of transition probability for Markov processes, it turns out. Now, it is just something like a Kullback-Leibler divergence between these transition rates, again, averaged over the marginal distribution. So it has a similar shape as in the case of stochastic differential equation. So the system that we got interested in is now a hybrid system that contains a discrete state and continuous states. So in this case, there would be a stochastic differential equation which is driven by a discrete noise process, so to say. So it's a linear one, and sort of this noise, well, I won't really call it a noise process, but the latent variable, the one that we don't observe X, but we observe X only noisily, but we have a system that drives it, which is also a stochastic variable, and that would be a binary variable, which follows a so-called telegraph process. So it's a Markov process that switches between a 0 state and a 1 state with certain switching rate gamma plus and minus. And so this is our prior assumption on that driving thing, and we have noisy observations of that X process. And so we got interested in that as a model for transcriptional regulation. So I wouldn't be the right person to explain the biology behind it, but my humble understanding is that this random variable mu of t represents a transcription factor activity which is unobserved and cannot be observed in experiments, which is assumed to have a strongly switching function. So you wouldn't really want to model it by a continuous process. It seems to be a switching one, could be in many applications the right one. And xi would then be the messenger RNA concentration of a target gene I, which is influenced by that transcription factor. And we would have noisy observations of that one. And we try to infer what mu is, and we try to infer what these parameters are. Sorry, lambda should also be a function of I. So this is the underlying model. So you look serious. That's okay. Right. Right. So we can again try at coming up with a backward-forward equations. So knowing that the joint process of the driven variables x and the driving variables mu, the joint process is Markovian. So if we look at the joint Markovian process of x and mu, so mu is binary, x is continuous, it's real, then the backward equation would be sort of, we would get this psi function would have a 0 and 1, it would depend on x, and it fulfills a first order partial differential equation. And the forward equation is again an ugly first order partial differential equation, and you can compute the posterior rates by solving the backward equation and then plugging and then make predictions putting in the forward equation. Just to convince you, you could do it and it looks a bit ugly, and if you have only a single x, so then it's just just a single variable and a partial differential equation just for a single variable, and you can do a numerical integration. That's what we have done. Now we could think about a variational approximation, and the variational approximation is based on the idea that the prior of mu is Markov, but the posterior of mu is not Markov. It was only the joint posterior of the driving of the binary driving noise and the real variables x. They are jointly Markov, but this mu is not Markov. But still, since the prior is Markov, we can try sort of try to find the best Markov approximation to mu, and then sort of avoid all these joint process that gives you all these partial differential equations. So we would use the variational Markov approximation, which would have, again, two parts. There would be the Kullback-Leibler divergence between the approximation and the prior, and there would be something coming from the data. And for the prior, we use the form that we have derived before. What's the Kullback-Leibler divergence between two Markov jump processes that flip between 0 and 1. So, and then we would have also terms that are related to the data, and for including them, we know that the noise, that the observations, of course, would depend on the observations, on the state variable at time t, and the state variable at time t can be computed in terms of this latent variable by solving the underlying ordinary differential equation exactly, and these two together sort of would then form our approximate inference process. Things are a bit more complicated, but we have sort of done a slightly suboptimal version of that by assuming, we would have to optimize all these posterior rate functions, and the way we've done it at the moment is we have sort of discretized them over time and placed two different versions between each we have discretized, we have two of them between two observations at the moment. So, and this is a comparison between, on a toy model, a comparison between the approximation versus the exact inference. So, so the underlying switching function was this. So you see you have just two switches only here in this case. So we have not many switches over the time interval. And what we see here is this is the exact flip, and this is the prediction that you get from solving the variational problem, and that would be the corresponding x variable. So that would be sort of the probability that you're in the 1 or 0 state, and the red things are the data, and here you get the uncertainty for your prediction on the variable x. And this is corresponding to the exact inference. Surprisingly, in this case, actually the uncertainty of the approximate inference method is bigger than the one in the exact case. And well, we don't have an understanding of that at the moment, but it seems like although you really do a very simple variational approach here, replace a non-Markovian process by a Markov process. Don't do a full variation, but only have a piecewise constant rate, posterior rate functions. Well, you get a reasonable result on these things. And so we've, yes, please. That's a good question. I don't know what it means exactly. Multi-unit. I mean, we were solving the backward equation, this partial differential equation for the marginal posterior exactly. So, good question. I don't know. Shouldn't. I don't know.
Or in process. Presumably, I mean, you have to solve forward, backward, then change parameters. So if you start with very bad parameters, you could get something.
Yeah, no, I'm not sure. I haven't looked at the real. I mean, this is only the mean prediction, of course. I'm not quite sure. I wouldn't expect that it's multimodal.
The dotted line represent the posterior uncertainty over X.
But plus or minus standard deviation?
Yeah, presumably.
Yeah, right.
That sometimes assumes that you're looking at something with one peak,
Okay.
right?
Okay, it's bad representation, perhaps.
Well, it could be a good one that was.
Okay, we can try that. I mean, sort of both programs run
We could find out very easily whether the marginals are all unimodal.
Yeah, okay.
I presume they are.
Yeah. Again, solving this backward-forward equation concentrates very much on the margins, of course, and well, okay, you could get correlations as well, but okay. So this is what the variational approximation would do in this case, and we've also applied it to real data related to. Sorry. Before I say that, that was a comparison with a corresponding Gaussian process prior over the switching thing. So you assume now, rather than having such a switching function, you put a different prior on the latent variable, which is not 0, 1, but which is a Gaussian process, of course. That is an assumption on the prior which really doesn't fit the data generating kind of thing, and in this case the result wasn't so good in fitting the data. Right, I think, I want to abstain from showing real data because I would have to understand them slightly more than I do, and really go to my last transparency to leave some more time for discussion. So about present and future work and why we still believe that there might be something useful in the variational approach. So one of the reasons is, as shown this morning by Yuan Shen in his talk, so the variational approach really gives us a probability distribution over paths. So we can use this really in a Monte Carlo method as a proposal for just changing paths. So it's not just a pointwise prediction, this is the marginal, it really gives us something that helps us to generate paths as proposals. So there's one thing, so we might be able to improve on the variational approach and sort of speeding it up, speeding the inference process up, going towards the exact results by using Monte Carlo. Well, there's another funny type of thing which I can't really explain at the moment. So you could even say, well, maybe even if the Q distribution is not a good one, it's not the true one, but you might still think in terms of frequentist types of errors, how well it might behave. And if you think in things of coming from computational learning, things so-called Peck Bayesian bounds that were used in order to give bounds on test errors for classifiers, for arbitrary classifiers, you can use a similar idea in the case of stochastic differential equations as well. And if you look at these Peck Bayesian bounds, they use Kullback-Leibler divergence between some prediction, some ensemble over predictors, and that don't have to be the right Bayesian ones. They have to be reasonable ones, and still you get some bounds on the performance of those ones. So that's an interesting direction to go. We started work on that. The other things I mentioned from the physics way of deriving a variational approach, this can be considered as the lowest order in a perturbation treatment of the free energy with respect to the difference between the true model and an approximation one. Maybe if you go to a bit higher order, you might be able to compute corrections and to correct for some of its deficiencies. That's something else that we want to do. A different problem is, which I haven't discussed too much, the variational Gaussian approach is not going to work easily for multiplicative noise processes. Where do you need multiplicative noise? Well, if you want to approximate, for instance, these prey-predator models by a stochastic differential equation, you automatically have state-dependent, that means multiplicative noise. For instance, you see this immediately if you are dead, if one of these species dies out, then of course it's not fluctuating anymore. It's not just 0 plus fluctuation. Dead means dead. Dead doesn't fluctuate anymore. And so also the noise is shut down in this case. And it means you have to deal with multiplicative noise in these type of models, but you can't treat them simply with a Gaussian variational approximation, because as I showed before, the Kullback-Leibler divergence between two measures that correspond to different stochastic differential equations would be infinite if they have two different diffusions. So if one diffusion depends on state, and the approximating one has to be constant because it's a Gaussian, it's a linear model with Gaussian noise, so those would never match and would have infinite Kullback-Leibler divergence, and one has to come up with a couple of new ideas. Well, some people say transform it away, but that doesn't usually work in interesting cases, and I don't have a good answer for that. Of course, this is always what everybody says. Let's go to higher dimensional systems. Well, we started working on it, and of course, in this case, we need to have good suboptimal variational parameterizations. Of course, we wouldn't be able to solve the full Gaussian optimal variational method, but we have to come up with ideas of parametrizing the models. And if you look at the picture, you see these means were just nice functions between observations. You could think of things, approximating the by spline functions or other things that have smaller number of parameters. You could think of covariance structures that could be approximated in a different way. So this is one of the directions that we want to go. Thank you very much. Yeah.
Your MCMC comparisons, were they just on the discretized model?
In time, you always have to discretize somehow in time.
Yeah, on the discretized path. And
Yeah.
you're not learning parameters as well in that case. It's just
yes, you could learn parameters as well, because you could compute the Bayes factor, the partition function as well.
Oh, I see, but not
Yes.
by not in a Bayesian sense by sampling those as well.
No. That was by computing the partition function.
Yeah.
Yeah. Yeah, Chris.
In your telegraph process example, the one with the
Yes.
binary and discrete as a continuous state, I had the impression that conditional on the this hidden new process thing is actually analytically tractable.
Yes,
so
deterministic.
It sort of suggests, so it suggests a sort of like Rao Blackwellization.
Yes,
So integrate out X and just deal with mu. Have you looked at this?
No. It seems, I'm not sure how to do that.
Okay, so we have a group photograph outside, and then we are going for lunch at the Churchill College, and we will meet here again at 2 o'clock.